So we're about to start something called the ideal gas law. In high school, Mr. Watts at Permian High School called this the pervert formula, and I cannot get that out of my brain. And so here it is, PV equals nRT, or as Mr. Bellin calls it, the Pivnert formula, not near as funny. So let's do a little bit of background info. So an ideal gas is what would happen if everything was perfect. So this is kind of like a theoretical gas. It's an imaginary gas that conforms to all of the assumptions of the kinetic molecular theory. So we know that it doesn't really exist, meaning not all of those points are always true for a gas. If they get super cold, they start to liquefy and they start to have attractive forces and they don't bounce off the walls like they're supposed to. So there is not a gas in the world that really behaves ideally. What we have instead is what we call a real gas. When a gas temporarily conforms to all of the assumptions of the kinetic theory, it can behave ideally for a moment. And so at that moment, we want to know what the ideal conditions are. When gases are at very, very high pressures, you'll remember they liquefy. And so they're not behaving ideally at that point. And when gases are really, really cold, they start to liquefy. So again, they're not having all of those elastic collisions and acting like a gas. So that's just some background terminology. So we already know the combined gas law. So on your notes, it has a place for you to write it up at the top of the page where it says we have already learned this. So in that white space, you're writing P1V1 over N1T1 is equal to P2V2 over N2D2. Don't forget our 2D2. So we've got this combined gas law. So if we wanted to, we could say, all right, so these are our conditions of our gas, whatever they may be. But if we wanted to compare those values to ideal conditions where things were just ever so perfect, look what we could do. What is normal pressure? Well, you should know that it's 1 atm. What is normal volume? Well, it depends on what quantity we're talking about. If we're talking about N being 1 mole, we could say 1 mole is equal to 22.4 liters of space. What is STP temperature? Well, just so happens to be 273 degrees Kelvin. So if we take the conditions that we're comparing to now, compared to the ideal conditions, that's what the pervert law is going to do for us. So check out this next slide where I filled it all in nice and pretty. In the little brackets of the second part of your notes where it says, so if we have the conditions at STP, watch what we can do. So go ahead and plug in all of your values into your parentheses. Your pressure, again, is 1 atmosphere. Your volume is 22.4 liters. Your 1 mole is what is true at 22.4, and at STP, the temperature is 273. When we plug in all of these 4 values and we plug that into our calculator is going to give us a value of 0.0821 atmosphere liter per mole Kelvin. That is the wackiest unit you're ever going to see in here. But basically, if you look, it comes directly off of the values that we plugged into our parentheses. We call this value R, or we're going to call it the ideal gas constant, which means it never changes. So these ideal values are always true when a gas is behaving ideally. But we just talked about that never happens. So here's the real story. So this is the one that I just know by heart because I know all of those values by heart that we just plugged into those parentheses. Well, if you wanted to go a step further and be an overachiever, you could also learn that R could be 62.4 if we were using millimeters and 8.31 if we were using kPa. I think that is a lot to put into my brain space. I already have enough up there. So I always choose this for R. And if this is going to be my R, then that means my pressure must be in atmospheres. The other thing to note is that my volume must be in liters, we must be in moles, and we must be in Kelvin. So if you're going to use this top value, which I highly recommend, then you just need to make sure that all the units that you plug into the pervert formula will match this R constant. So in the middle of your notes, this is the pervert formula. This is the ideal gas law. PV equals nRT. So it's kind of like we're doing the combined gas law, but our second values are all hidden in this R. So it's kind of like these are all of our ones, and everything that's a 2 is hidden in R. But we don't actually write down that 1. So erase those if you just copied me, because I don't want you to get confused. There are no 1s and 2s, so they're kind of easy to spot. So our pressure, like we said, whatever your pressure is, it just needs to match your value for R. I always use R as 0.0821 atmosphere, liter, mole, kelvins. And then your temperature is K, and your volume now has to be in liters. So if we look at this first example, it wants to know how many moles, which is N. Of 120 liters, there's my volume, of SO2, sulfur dioxide, at a temperature of 40 degrees, which we can't use. So there's my 313 Kelvin, which is my T, and a pressure of 1.85. So there is my pressure. So they're asking for N. They gave you VT and P. So since they gave you no secondary values and they didn't mention STP, we know we've got to use the pervert formula. So here we go. PV equals nRT. We are looking for moles, so I'm going to put a box around moles. Nice thing is there's no fraction. We need to isolate N by dividing both sides by RT. So now my new formula is N is equal to PV over RT. I go plug in my values. My pressure is 1.85. My volume is 120 liters. My crazy whack R, don't you dare leave off those units, I'm watching you. And my temperature, which is 313 Kelvin. My favorite part, cross everybody out. You can only cross them out if they are on opposite sides of a fraction from each other. For example, atmospheres in the numerator, atmospheres in the denominator. Liters in the numerator, liters in the denominator. Now, this is weird. Kelvin's in the denominator, but it's on top compared to this Kelvin, which is in the denominator of a denominator, so they are actually allowed to cancel. So now what we have left is moles in the denominator. The denominator, if you take the inverse, just trust me when I tell you, the answer will be in moles. So when we crank this out in our calculator, we find out that N is equal to 8.6, because of sig figs, because of that 120 moles. And since they gave me a chemical, might as well slap it on the back. Sulfur dioxide. So that is how many moles of gas I collected at these conditions when compared to an ideal gas. All right, next up, example 2. So pretty similar. At this point, you're just solving for whatever variable I give you. So in this example, they want to know what is the pressure. And they specifically told you in millimeters. Exerted by 85.5 grams. Uh-oh, that's a nothing. And so that's not any of my variables. So I've got to figure out how to change that into N, but I'm going to have to train track it. I've got my 27 degrees, which I can't use either. Add my 273 to get 300 Kelvin. There's my T. And it's in a 15-liter container, which is my V. So we have a lot more going on in this one because the units aren't as friendly. So rather than obsessing over all of that at first, figure out what do they want. They want pressure. Let's give them that first. So we say PV equals nRT. We need pressure to be by itself, so we're going to divide both sides by volume. And so we say that pressure is equal to nRT over V. Now let's see what we have that we can plug in. We have R. It's always 0.0821 atmosphere liter mole kelvins. We have our T, which is 300 Kelvin. And we have our volume of 15 liters. So here's the problem. We don't have N, but we can get it easily. I'm going to come way up here and take this 85.5 grams of carbon dioxide, do a quick little train track, and say that there's 44.009 grams of carbon dioxide in a mole. So when I type that into my calculator, I find out that it's 1.94 moles. Well, now that's going to be my N value. So that is going to come and get slapped right down into there. So 1.94 moles. So I've got all my slots filled. I'm going to cancel numerator, denominator, numerator, denominator, numerator, denominator, which means when I find pressure, it's going to be something in atmospheres. So we plug that in, and we find out that it is 3.2 if we wanted to do sig figs and keep it at 2 sig figs because of the 27 degrees. So we've got these 3.2 atmospheres, but if you'll notice, they asked us, what is it in millimeters? No problem. We know that an atmosphere is 760 millimeters of mercury. So we have a new answer. Pressure is equal to 2 sig figs again, 2,400 millimeters of mercury. And that is a crazier version of an ideal gas law. So you had a lot going on. You had to do 2 train tracks to make this whole thing work. Check your units, check your units, check your units. And so we're basically comparing this gas at 27 degrees in a 15-liter container to a container that is at STP, which is R. And so that's what we're doing in an ideal gas, is comparing a real gas to an ideal gas. Honestly, I think it'd be insulting at this point if I did this entire problem for you. I want you to try this one on your own, and I'm going to tell you that your number of grams should equal 0 point something. And there's an actual digit here that is not a 0. So the answer is not 0.061. So if that's what you got, you're not finished yet, but you're on the right track. So see if you can get me a number that is better than that. All right. Now, here's where it gets real. They want to know what is the molar mass of a gas if 0.628 grams of the gas occupies a volume of 150 milliliters at 25 degrees and 7,456 millimeters of pressure. There's a lot wrong with this. All right, so let's analyze what we've got so far. We have the grams. Awesome. Of what gas? I have no idea. And so I cannot train track those grams and turn it into moles because I have no idea what the molar mass is. I'm trying to figure that out. So this is not usable at the moment. I've got a volume of 150 milliliters. It has to be in liters. So you should know how to do that and end up with 0.150 liters at this point. My 25 degrees Celsius is my 298 K. There's my T. And I've got this millimeters of pressure, which I'm going to have to get rid of later and change it into atmospheres. So I've got a volume, a temperature, and a pressure. I have an R. So what we're going to have to do is come up with moles. So go with me here. On this slide, I'm just going to show you how I totally rearranged this pervert formula to solve it for molar mass. So right now, you're looking at that formula saying, I don't see the word molar mass. I don't see a symbol for molar mass, and you're totally right. Well, one thing you should know is when you're trying to get moles right here, you always start with the given number of grams, and you divide that by the molar mass in grams to get moles. So we could effectively say that moles is really mass over molar mass, which I abbreviate capital MM. So now we have PV is equal to mass over molar mass, RT. So if I need to solve this for molar mass, which is on the bottom, you know my favorite, I'm going to butterfly it, and end up with PV times molar mass is equal to, I'm going to abbreviate this mass up here with an M, mass RT. Now mass and molar mass are different. The molar mass of carbon is 12.011, but the given mass, I might give you 3 grams. So the given mass and the molar mass are not the same value. So again, I still need to solve this for molar mass. So I divide both sides by PV. So now I've got molar mass is equal to MRT over PV. That's hard to remember. So I have a trick. So what do you get when you divide mass divided by volume? You should remember from 8th grade that that is density. So if that is density, really I can take that out and say that molar mass is equal to density RT over P. Now, why is that easy? Because I walk around saying all the time, molar mass is dirt over P. Molar mass is dirt over P. Molar mass is dirt over P. Did you learn it yet? That's hard to forget. And if you need the mass and the volume, all your brain has to do is say, oh, that's density. I can cross that out, add in my M and my V, and then I've got that formula. That's right up there. So really, I only want you to know 2 formulas. I want you to know pervert, which is PV equals nRT, and I want you to know molar mass is dirt over P. And if you need something in between, you just can pick and choose how you rearrange, and it's a whole lot easier to know those 2 than all of the rest of the stuff. So let's take a look at this on a clean slate. So what is the molar mass of a gas if you've got this 0.628 grams of the gas occupying a volume of 150 milliliters at 25. So let's start plugging in. Here's our new formula. Molar mass, here's my density, dirt over P, but I don't need density since they didn't mention it. And I'm going to start plugging in, and I'm done. The hardest part was rearranging the formula. So the molar mass is, I don't know. The mass they gave us is 0.628 grams. Your R is 0.0821. Don't forget the units. Love that part. And your temperature, we said on the previous slide, was 298 Kelvin. We're going to divide by volume, which is our 0.150 liters, because we had to move that decimal, 1, 2, 3, to make it into liters. And now this guy, I've got millimeters, can't use it. So 7,456 millimeters. And the reason I can't use it is because if I have millimeters here, atmospheres here, I'm not going to be able to cancel them in a minute. So I'm going to get rid of it now. 760 millimeters of mercury in an atmosphere. And that's equal to 9.811 atmospheres. That can go up here for our pressure. 9.81 atmospheres. That is an insane amount of pressure, by the way. And so we plug the whole thing in, and we find out that our molar mass is equal to 10.44, unless we did sig figs, and we'd round to 10 grams per mole. Let me show you how I got grams per mole. If I go up into my handy-dandy little formula here, my liters cancel, my atmospheres cancel, my kelvins cancel. I'm left with grams in the numerator per mole in that little denominator. So that's what goes on my answer. Now, they did not say identify the gas because we have no idea what gas that is. If it was an element and we were looking for something close to 10, we don't have a gas that has a molar mass close to 10. But it could be any kind of a thing with a molar mass of 10. They didn't ask us for that. And so all we know is that this unknown gas has a molar mass of 10. That's it for tonight, Chem Nerds. Thank you so very much. See you tomorrow.